So let's reiterate a little bit that we talked about in last class. We'll review just a little bit and then get into some more content and see mostly examples today. We'll finish up these slides and then look at examples. There won't be slides for today's lecture though, if you're looking for those on the website. All right, let's do this. So last time we introduced cryptographic hash functions, and we specifically talked about SHA-256. The idea of a cryptographic hash function, this is meant to be used as a one-way function. So we have some string, some data that we want to kind of hide from people is effectively what we're doing. And in our case, for our application, we're hiding passwords. And then we're going to hash them and store just the hash of a password, which is this text after it goes through our cryptographic hash function. We're only going to store this hash, and this hash has the property, or at least we believe, just like with cryptography, we don't know that these hashes are secure. It's not proven that they're secure, but no one's been able to find, or at least nobody's publicly shared, an algorithm that can undo these hashes. There are some theoretical attacks on SHA-256 in particular, but nothing practical that's known to the public at least. So we're going to assume, at least for our purposes, we'll just assume that there is no attack, so we don't have to go down that road of theory and talk about all that. We'll just assume that this cannot be reversed. You can't go from the hash back to the password. SHA-256, I'll show this calculator. I had this open in the browser, but SHA-256 is what we're going to use. I won't go into the details, but it's a series of bit level operations, or byte level, I suppose, that's effectively scrambling the input and giving us a fixed length hash. This is very easy to compute. I mean, the logic here is obviously fairly complex, but it's very quick to compute. Since these are all byte level operations, these are all CPU. These are all things in the CPU instruction set. So these are very, very fast operations. Hashing is a very, very fast thing, which is something we want. We want hashing to be fast. It's one of the properties we definitely want. But it's very difficult or extremely slow to undo the hash, and practically impossible for all practical purposes. Impossible to go backwards through this thing. The data is just scrambled up in such a way that we can't just run this function in reverse. It's not feasible to do that. So let's see this. I do want to talk about the attack and then do both demos at the same time. So there is one big problem. I mentioned this at the end of lecture last time, is that you don't have to undo the hash. Given a hash, you don't have to strictly reverse the computation of SHA-256 or any hash function, because you can run what's known as a brute force attack, which is effectively just guess and check. Since you can run the hash function, you can compute hashes very fast. You can run the hash function in the forward direction very easily. There's nothing stopping an attacker, no matter how sophisticated our hashing gets, nothing stopping an attacker from just trying a bunch of guesses, hashing those guesses, and then checking if the hashes match the value that they're trying to break. So this attack is always going to exist for our applications of hashing, because we need that property. We really want that property of hashing to be not only be feasible, but to be fast and easy to compute. So this is always going to be an attack that exists. So even though we can't undo a hash, this attack is always going to exist, and this is why we still have to make sure that our passwords are strong, because if you get that hash and you have a weak password, it's going to be attacked. So that's all stuff that we talked about right at the tail end of yesterday's lecture, so I wanted to reiterate some of it. So we'll be talking about it quite a bit. While we're in here, if anybody has, actually no, let me do it this in the other order. But I can still ask that question. If anybody has a preferably appropriate 5-letter word that we can hash. We can use that for our examples. So here I have some Java code pizza. Perfect. Let's so we're going to take the word pizza. I'm going to hash that, and I'm going to grab this SHA-256 hash value that I computed on an online calculator. So just notably, it's something that's not touching my code at all. My code did not see that word that was hashed. And we'll put that right here. We'll use this in a little bit. I gotta undo my salt. We didn't talk about salting yet. So I have this hash of the word pizza. And just for good faith, I'm going to take pizza and compute that hash in Java. I'm going to get a SHA-256 hash function, the SHA-256 hash function, or rather an implementation of the SHA-256 hash function, and compute the hash of pizza. And if all goes well, I should get the same exact hash value. So if I grab this hash that I computed, put it right next to this hash, we should see the exact character for character, exact same hash. This is how password authentication works. The hash is always going to be the same. SHA-256 has a very clear definition, and no matter what implementation you're using, you should always get the same exact hash value. So if these hash values match, that's when we would say, okay, you're authenticated, you're good to go. I can't do that. You're allowed to access this system. If I have even one character wrong, maybe I have a capital I instead of a lowercase I, and I run this again, the hash I get is not just going to be a little bit different, it's completely different. And this is another property that we need of hash functions. This is why if you type your password even just a little bit wrong, we don't want an attacker to gain any information from that hash. We don't want the hashes to be similar and have the attacker go, well, it looks like I'm getting closer, and then doing some hill climbing attack. They could really narrow down the search space very quickly. So they gain no information, even if they're really close to your hash. This is also why if you type that password in just a little bit wrong when you log in, if maybe you don't think that this these days, but at least when the internet first became a thing, people would be like, come on, I was so close. Can't you just let me in? Well, no, we can't, because we have no idea that was close. The hashes are completely different. So there's nothing we can do for you there. So with this hash of pizza, let's not compute the new hash again. And what I want to do is run an attack on this hash. So this hash, my code doesn't know anything about this hash. It came from the internet. I used an internet calculator to compute this. And then I'm going to put this into my attack, give it some valid alphabet of where the characters of the input came from, and some salt, again, that we'll talk about later. It's just empty string right now. And what my brute force attack is going to do is try every possible string of this character set, every possible combination, starting with combinations of length 1, so just single characters, and then all combinations of length 2, all combinations of length 3, and it's going to compute the hash of that string that it's checking, and check if it's equal to the hash that I'm trying to break. So it's just a strict guess and check, and returning that value if it guesses it right. Hi, Bear Costume, what's up? Do you have words? Oh, god damn it. I'm assuming that was a bot. If you're not a bot, sorry, email me, I guess. All right, so I'm just guessing every possible combination of characters given an alphabet, and then my alphabet is the lowercase English letters in this case. And I can change the alphabet. I have multiple different alphabets here. So let's run this thing and see how long it takes to crack a password of length 5 using only lowercase letters. With a really crappy attack, by the way. Also. And we cracked it. It took, I don't know, not too long. That's not a scientific measurement, but not very long to crack that hash. This is obviously a very weak password. And I was able to crack it with nothing sophisticated here. I'm just trying every single possible combination, and I'm being a little sloppy with my things like my memory management and my computation. I'm converting bytes to strings, which is a little bit expensive. I'm doing a lot of sloppy things here. I'm still able to crack this password in a pretty short amount of time. So this is our concern. So I just, effectively broke SHA-256. I mean, not effectively, but I could convince someone who doesn't know what they're talking about that I just broke SHA-256. So this is a concern. This is a valid attack. This is something we can do. This is something that can be done, and we need to do something about that. Like this is a big concern. So what we want to ask, maybe add a, oh yeah, I could add a timer to the code. I actually have another example where we're going to talk about the timing a little bit more. That one I just want to show that an attack is possible. I want to show you, make it real that, hey, we can break these things. Here it is, right in front of your face. I just broke a password. So I'm not too concerned with the timing there, but you can get a rough idea. And then each time we add a character to that, increase the length of the string. It's going to take longer, of course. But in the other demo, I want to talk about what kind of a real measure, more of a scientific measure of that. What's the worst case time complexity of the function? I mean, strictly speaking, infinite, if I'm not given a valid hash, but I don't think that's what you're getting at. And it depends what you're measuring it in. But we're actually going to talk about that at some degree. Is the brute force code available somewhere? Would be interesting to look it over. No, it's not available, but you just saw the whole thing. There's not a whole lot to it. It's, I would put this under expectations. Like, you should be able to do this. Computing the SHA-256 hash, if you Google that for your language of choice, there will be some way to compute SHA-256 hash. And my brute force, it's effectively the problem of finding every permutation of a set or of an array in this case. How do you find every permutation? I'm going to take one letter out of that set and append it to what I currently have, and then run that recursively to keep appending more and more characters. I have recursion in a loop that's going to get me every possible combination of characters in this thing. Then I just check each one. So there's not even much going on. This is a very low brain attack, but it is effective if the passwords are very weak. And that's the whole, like, there's not much there. But no, I'm not going to post this online. Not really comfortable having attack code out there in my name. I guess it'll be in the video, but still. So let's talk about how long it would take to crack something. And for that, we need to talk about something called entropy. And for objective 4 in the current homework 8, you do have to have a token with at least 80 bits of entropy. So what does that mean? Let's talk about that and see what bits of entropy is and how you're going to achieve that 80 bits of entropy. So entropy is synonymous with the amount of uncertainty that a value has. And in what we're going to measure here is the number of guesses that somebody would have to make in order to guarantee that they guess your password. Or according to some criteria, how many total passwords do exist with those criteria. So for example, if we have just one single lowercase letter, our entropy is 26 because it would take 26 guesses to exhaust the entire search space and guarantee that you crack that hash if you know that it's only a single lowercase letter. If you have 2, this starts increasing exponentially. 2 characters, you have 26 squared, 676 guesses, we're looking better. If we start adding uppercase and lowercase, 52 squared, we're up to 2704. And as you can imagine, and as we're going to see, these numbers get big very quickly. So instead of looking at the raw number of guesses, we're going to take the log base 2 of those values, and that's our bits of entropy. So the log base 2 of this value, that's going to be the bits of entropy. So however many total guesses you have are required to find that, to crack that token, the log base 2 of that has to be greater than 80 to be able to fulfill that criteria. Yeah, SHA-256 hashes are stronger than SHA-1 hashes. SHA-1, I believe there are practical attacks that can undo the hashes that make SHA-1 not secure anymore. So we don't, if we're concerned about that, we don't use SHA-1 anymore. SHA-1's still used for some purposes. We saw that in signing, in the signatures for certificates. We saw SHA-1 there. We saw SHA-1 in WebSockets, but we weren't concerned with somebody undoing that key and finding out the key for a WebSocket. We just weren't worried about security at that level. So we'll still use SHA-1 in times in the world. But if we're hashing passwords, we want to use SHA-256 or better. Yeah, SHA-1 should not be used for passwords anymore. I'm pretty sure, I mean, I could be misremembering, but I'm pretty sure there are attacks on SHA-1 that you can undo a SHA-1 hash without too much trouble. So let's see an example of this entropy. I'm going to go to this other file here. If I'm clicking on the right window. OBS didn't understand what I meant, understandably. And I want to measure this bits of entropy based on some criteria. So let's go to our example that we just saw. 1 5-letter word using only lowercase characters. I want to check how many possible combinations of these 26 characters of length 5 can I create. What's the bits of entropy of that? And, well, I'm actually computing the entropy first, which is 26 raised to the 5th, and then the log base 2 of that, which I have here. Simple math, exponentiation, and then the log base 2. I don't have a convenient log base 2 in Java, so I just did some properties of logs to get the log base 2. Gives me the bits of entropy, and then I'm going to take that bits of entropy and raise 2 to that power to kind of do what I did before, but in reverse, to figure out how many total guesses there would have to be able to guess that value. And I have a little bit of rounding here. I believe I take the right here. I take the ceiling of the bits of entropy because the way I'm doing this needed an int. It's not too much rounding, so I'm comfortable with that. To shift 1 bit of entropy, it's at most going to be off by a factor of 2. But when we see the numbers, you'll see that isn't really going to matter for us. So we get those bits of entropy, and then I want to compute how many hours it would take somebody to compute. With my years to crack function, you'll see, spoilers a little bit there. I'm going to assume that somebody can compute 1 billion hashes per second, which is completely reasonable. Our processors run billions of operations per second. So if you have a pretty good processor or even a GPU where you could probably exceed 1 billion, this is a very reasonable number to be able to compute that many hashes. Since we can already compute billions of operations per second, it's how many operations can you get the hash down to. And we can get pretty fast. If you're familiar with Bitcoin mining at all, Bitcoin mining has pushed this quite a bit. The whole crux of Bitcoin mining is computing hashes very, very fast. They have dedicated hardware and GPU acceleration, all kinds of cool stuff. to be able to compute hashes very fast. An attacker takes some of that technology, throws it at password cracking. 1 billion is a very reasonable number. So let's run this first. And that password, if that were our password, just some random 5 characters, takes 0 hours to crack. Not very many hours. As we saw, we cracked that in less than a minute, so we expect that. So we expect that not to be a big one. And our bits of entropy here, 23, much less than that 80 that I'm saying in the assignment. So let's start playing around with this a little bit and say, what if we had uppercase and lowercase letters? 0. What if we have length 8, common minimum for passwords? Now we're finally starting to clock something. We get 20 hours to crack this. What if we add in numbers? $78 hours. It's taken them 3 days now to crack this password. And what if we add in special characters? I'm going to assume there are 28 of them. And say that we have an alphabet size of 90 characters to the 8. Now it's taken them a decent amount of time to crack this thing. So using these password criteria, we can up the entropy of that password and make it a lot harder and take a lot longer for somebody to guess that password. SHA-1 just shouldn't be used. Since SHA-1, I mean, you can look it up and read about it to verify, but I'm pretty sure there's an attack where you can actually take the hash, a SHA-1 hash, and reverse it. The algorithm itself is actually broken. There are attacks. You shouldn't be using SHA-1. And why would you want to? You have SHA-256 just sitting there on the shelf. Why even bother with SHA-1? It'd just be a silly thing to do when the community is saying, hey, that's not secure, use this other one. Why fight that? But we'll notice this still isn't that large of a number, and our bits of entropy is way short of that 80 that I'm talking about on the homework assignment. So let's see if we get this up to, say, 10 characters. Let's see what a stronger password would be. And we can see that power of exponentiation. This is going to increase significantly. And at this point, I want to switch to the actual years to crack. I'm going to add in 24 hours and 365 days. That would actually take this person, if you have a purely random string with all the uppercase, lowercase, numeric, and special characters, and its length 10. You have 64, almost 65 bits of entropy, and it's going to take them just by adding 2 characters, mind you, to the length, we get that power of exponentiation. It's now going to take over a millennia for this attacker to be able to crack your password. We get huge amounts of entropy by increasing the length of that password. And we're still only at 67. If we go to our full 80 bits of entropy, it's going to take a long time to crack that thing. 80 bits of entropy is kind of this rule of thumb where if you have 80 bits of entropy, you're secure. Nobody's going to take 2 to the 80 or amount of time or amount of computations. Nobody's going to take that long because they just don't have that much time. There's not that much time out there. And at this point, we can even say, let's say that these attackers can compute 100 billion, a trillion, 100 trillion. Let's just say 100 trillion. Comments sometimes lie, code never does. If I don't update that, comments lie. Even if they have 100 trillion computations per second, maybe they have a whole botnet all with high-end GPUs. They're using every machine on the planet. They have tons and tons of computational power available to them. Actually, I don't know if 100 trillion really captures all of the machines on the planet. But if they have a ridiculous amount of computation, it's still taking almost 4 centuries to crack this password with 80 bits of entropy. That's not going to happen. It's just in absolutely prohibitive amount of time. And what if we go back to our passwords, our full uppercase, lowercase, numeric, special character, and have a random password of length 16? Hell, let's give them a little more computational power too. Quadrillion? I don't know how to spell. Quad. Let's even give them more computational power. They can have as much computational power as they want. I'm not concerned. We have 103 bits of entropy, and even with 100 quadrillion attempts per second, which is getting to be a pretty high amount, they have to have a lot of resources. They're still not going to crack your password. But if you have that weak, and we can go, let's push it one further. And we very quickly get to this area where, let's see, 1,000, a million, a billion, a trillion, 0.4 quadrillion. Like, we're getting into the range where the sun is literally going to burn out before they're done cracking your password. So I'd say you're pretty secure if you have that many bits of entropy. If you got 130 bits of entropy, you're fine. Nobody's cracking that password. But if you have one of those really crappy passwords, hell, even if you have 8 characters, that's not even going to be a blip on their CPU. That's going to be cracked immediately. So this is what I was talking about last time. If you have that weak password, and this attacker is never going to crack those strong passwords. There literally is not enough time in the universe to be able to crack, or at least in the solar system, to be able to crack that hash. They're just gonna quickly try and then move on. But once they find somebody with this password, they're gonna crack that thing immediately. Hell, even if it's 90. Of course, I gave them 100 quadrillion. That's 1,000, million, billion. Let's go back to a billion. Since my comment lies, I'm just going to get rid of it. Zero. I think we might have already computed this one, but just a reminder. This is down to hours, though. It's feasible to crack that one, even following all the password criteria. Even if you have a perfect password of length 8, they can still, this is hours, they can still crack that thing. They still have that potential. But don't most passwords that people use for social media have length 8 to 10-ish? Yep, probably. I would imagine the vast majority of passwords are length 8, or whatever the minimum is for the site you're visiting. I would imagine that. So even if they have a perfect password, but it's length 8, and somebody with just a standard PC or laptop is cracking their password, even with perfect entropy, it's going to take that many hours to crack that password. Let's do days. How many days is that? $52 days, so like 2 months. So they really have to, and part of my point of this is they would really have to want to attack you specifically. If they're just after anyone, they're still not cracking this password. But if they're after you specifically, they're going to get you eventually. They're going to get you. If they have your hash. Which do get leaked. You see database hacks in the news from time to time. Attackers can get your hash. They'll get it sometimes. It's not 100% guaranteed that your hash will be private. It's why we hash. It's why we don't store passwords in plain text. Don't the site like Google lock you out after 5 attempts? This isn't going through the app. This is after you've attacked the database. You have the hash in your control, and then you can put that hash into your attack script like this. This isn't going through the app at all at this point. It's after you get the hash out of the database, compromise that part, then try to crack the hash offline. Yeah, exactly. So, yeah, for most attackers, I assume it comes down to profitability. If it takes too long to crack a hash, that's why I'm saying they have to really want to go after you. So, for example, if it's a celebrity, maybe they're going to take that time to go pry into their personal life and be a scumbag like that. They're going to take that couple of months to crack that hash. But in most cases, for regular people, they're probably just not going to bother because there's just nothing in it. Like, what are they going to get from you? What are they even going to get from me that matters? Probably nothing that they're going to profit off of. Like, it would suck for us, but it's not going to help the attacker. Like, they're not going to be able to hold me for ransom for like $1 million. I don't even have $1 million. Like, there'd be no point in them doing that. Unless they just want to fuck with me specifically. Maybe a disgruntled student or something. There has to be a reason why they're trying to guess the hash. Yeah, exactly. But I'm not sure what. Not the original password. Okay. Yeah, so they would compromise the database, get your hash, crack your hash, and then once they crack your hash offline, then they would go back to the app and enter your username and password, and now they have access to your account. It would be the full thing, the full idea of what they're doing. So with this entropy, there's one huge problem with this. Oh, and just to wrap up, for the objective 4, take your alphabet size and the length of your token, raise the alphabet size to that length, randomly generate strings from that alphabet, and then as long as that exponentiation, the log base 2 of that exponentiation is greater than 80, you have that entropy, and then randomly generate your tokens. But there's one big problem with this brute force attack, or with that brute force logic with the entropy and everything, is that it assumes that we have purely random passwords. That the user is taking the uppercase, lowercase letters, numbers, special characters, and generating a purely random string based on those criteria, which is pretty much never the case, because you can't remember those purely random strings. The problem is, an attacker is going to take advantage of the fact that we tend to think of passwords that are easy for humans to remember and not passwords that have a lot of entropy. This enables what's called the dictionary attack, where instead of just guessing purely random strings like I am in my attack, what they're going to do is start with the most common passwords like we saw last time, make variations of those, make common substitutions that people like to make in their passwords. To get that special character, you're just going to replace an A with an at, and then it's easy to remember. They're going to attack like this. You're never going to get that full entropy unless you use a password generator, have something storing those passwords, something like that, password management software. Aside from that, you're not going to get that full entropy that we saw. It's not going to take that long to crack those passwords because they're just going to try what people tend to use as passwords. And it's going to take a lot less time than the years, centuries, all those numbers that we saw. It's going to take significantly less time to crack that. Whereas your tokens, by the way, just a side note, the tokens will have that full entropy because you'll programmatically generate those tokens, generate random strings. But passwords that humans come up with are usually pretty weak, even with the criteria that are out there. So it's more bleak than we saw in that entropy example. It's a little more bleak than that. But if you want to secure your own accounts using some password management software that's generating those very, very strong sun burning out passwords, you want to compute those and then have the software remember it. Of course, there's another level of security. You have to trust that software, but but at some point there's going to be some assumption of security at some level. So let's talk about rainbow tables. So rainbow tables, this is an attack that used to be very popular. I very briefly explained this last time. I think it actually was during the Q&A anyway, so it wasn't really strictly part of lecture. So rainbow tables are effectively going to trade off pre-computation and memory for fast breaking of hashes. So how a rainbow table works is it takes a let me back up one step. So one attack that we could do is pre-compute every single hash that we can, just hash every possible combination of characters, and then put all those in a big lookup table, and then a lookup table that maps hashes to their inputs, and then take that hash, when we have a hash that we want to break, just look it up in that giant table. Problem is, that table is going to take more space than we have on the planet to be able to store, even if you just go up to like length 10 strings. So rainbow tables are getting away from that space issue. What a rainbow table works is says instead of storing every single hash, we're going to store chains of hashes. We're going to start with some hash value and then hash that hash value, hash that again, hash that again, hash it again, hash it millions, billions, trillions, however many times they want, depending on the parameters of the specific table they're generating, and then only store the first and last hash in that chain. So they can effectively store, quadrillions probably, quadrillions of hashes just by storing 2 hashes, and those 2 hashes represent that chain of hashes. And then they do this over and over and over again, pre-compute all kinds of hashes, have all these pre-computed hashes, and then store them all as the first and last value in the chain. Now when you have a hash you want to crack, you're going to hash that hash it again, hash it again, hash it again, keep hashing it until it matches one of the end points of a chain. Once it matches one of the end points of a chain, you know which chain this hash belongs to. Go to the start of that chain and keep rehashing that start of the chain until you get the hash you're cracking, and then back up 1 hash. What was the input that got me the hash that I'm cracking? That's your password. So this is a really effective attack since you can have tons of processing power computing these tables for years, even to generate these massive rainbow tables that take up gigabytes of memory. Gigabytes, even when just storing the start and end chains. You have tons and tons of hashes represented here. And then store all those rainbow tables, and attackers would share these rainbow tables. I think you can still just download these things on the internet. You can go out there and download a rainbow table and then run a rainbow table attack. So this is very, very bad. Then once you have a hash that you want to crack, it's very quick to crack that hash because you're leveraging all that pre-computation. So we want to not allow this. This is a very bad thing to have these rainbow tables attack. And this is finally where salting comes in. So we're going to salt the hashes, which I was talking about quite a bit last time. Let's talk about what that really means. Is we're going to generate a random string that's going to be stored in the open. So anybody compromising the database and obtaining the hashes is also going to have this salt. We're going to store the salt in plain text along with the hash, but we're going to append this salt to the end of the plain text password before hashing. So we have this string that everybody knows, a very random, can be long string, that everybody knows about it, but it's going to be appended to the end of the plain text before hashing. And then when somebody authenticates, somebody goes to log in, we're going to append that same salt to the end of the password that they inputted, hash that, and then look it up and make sure that matches what we have stored. So since this is stored in the open, all the attackers know about this hash, and they can add this to their attack. So, for example, if I if I compromise the hash, I also have the salt, and I'm just going to append this salt to the end of every one of my guesses. So I don't gain any entropy with this salt. There's no security in that sense, because the attack can handle the salt, and I could append the salt to the end of pizza, compute the hash, and run it. For the sake of time, I won't show that one. Maybe I'll show it during Q&A if someone asks. But with the salt, we can still crack the passwords. Somebody could still crack the password in effectively the same amount of time as they could without the salt. But what this does do is completely shuts down the rainbow table. So when you have a chain of hashes, the only hashes, since the hashes are the inputs, the passwords that you're trying to break themselves, the hash that's going to be a valid password has to end with this salt, which is going to be almost zero of the hashes in this rainbow table. If you have 80 bits of entropy in your salt, which is easy to get, which you certainly should have in a salt, if you have 80 bits of entropy, that's 1 over 2 to the 80 hashes in that rainbow table that are actually valid, that can actually be a valid guess. So this completely shuts down rainbow tables by adding these salts. It also gives us this feature where an attacker has to attack one specific hash at a time. So if they were running a brute force attack and they have a database full of passwords that are not salted, hashes that are not salted, what they're going to do is each time they take a guess, they can look and say, is this hash value anywhere in this database? Is it anywhere in this set? Check every single hash and then see how many of them I just cracked, how many of them had that password. Very effective attacks. Salting gets rid of that. Since you have to append the salt to the end of your guess, you can only attack one password at a time when salting is being used. And salting is very standard these days. If there's any organization out there storing passwords and not hashing them, storing them in plain text, that's awful. But I'd say even if they're hashing but not salting, that is still very bad. This is pretty standard. This is standard practice. You're always going to salt your hashes these days. Just what we do. For all of this stuff, which I kind of regret, but I'm not going back on it, the homework, you can pull in the bcrypt library. This library has implementations in any language that you're going to be using. And this library will do the hashing, the salting, and all this good stuff, and a lot more that we won't use. A lot of security stuff. This bcrypt library is one of the standards out there. It's a very fantastic library. And I have just a quick example of code here. This is in Python, of using bcrypt and Mongo for what it's worth. We're not really talking about databases anymore, but with it is reset password. So when somebody sets their password, they're going to provide two passwords. I'm going to make sure that I saw this yesterday when I was looking these over. I'm like, you know what? I'm going to leave it in there. It's pretty ubiquitous with programming. Most of us have profanity in our code somewhere. I just wanted to show you that you're not alone in that. So if they have a valid token, so I'm giving them a token saying you're allowed to reset your password. We can talk about that next time if it comes up or during Q&A. If they have a valid token in the database, I'm going to check if their passwords are the same. And if those passwords are the same, and I only have one criteria I'm checking here, is just the length of the password. If the password is too short, I'm going to tell the user, hey, you got to have at least 8 characters. And if they do have a valid password, that's where I'm going to enter that password in the database, the set password method, which is going to pull in my... Oh, I have another method. It's going to enter my into my database. It's going to update that user's password, and hash password is where I want to be. This is where I'm going to use bcrypt, which has all of this functionality built in. I'm going to hash this password. I'm I'm going to give it the password that I want to hash. And I also want to generate a salt with the same library. So I'm going to get some salt, random salt, and hash this password with the salt. And the way bcrypt works is this hash value isn't just the hash, it's actually the salt and the hash of that salt. The salt of that hash all rolled into one. And if I look at this, oh my goodness. I can't even type right now. Oh. Focus. All right. So if we go into our database, we have these collections that are used to run this app, and I want to go into. I went too far. Screw it. I'll just type it. db.iq users.find. And in the spirit of security, I'll filter based on username and attack myself. So here's my user account. I'm an admin, yay. My user account for the system. Some information we don't need to talk about today. But what I want to show right here is that bcrypt password. When we go into the database, I have my username and the password, the salted hashed password for this app. And that's what's going to be stored in the database. We don't have any plain text here. We don't have any, and we don't have just raw hashes. This is encoded to have the salt and the hash in the way that bcrypt stores values. So you could take this hash, extract the salt, run some attacks on this, and you could try to hack my password. That's why I don't want to show anybody else's account except my own, because you can use this information to try to break into my account. Which, if you do, I'd probably give you extra credit. Let me know if you break into it, if you crack this hash. I'll give you a hint. My password isn't super strong. It's actually feasible that you could break it. But you can't affect any student data. You can't do anything with the system. Plus, I haven't told you what the system is, so you have a lot of work to do. You have an uphill battle. But if you do, yeah, I'll give you extra credit for that. But this is what's stored in the database. This is what an attacker gets, and then the attacker has to try to crack this to try to get that value. The first one is typing this manually. You can go back in the video, and you got plenty of time to do it. But yeah, first step is just the tedious task of typing this instead of cut and pasting. And I know there's something else I want to show. Redirects, email verification. I don't really need to show that today. I feel like there's one last thing. You take a screen. I mean, it's recorded. You just go watch the VOD. I thought I had one last quick thing. I don't have anything else that's quick. So that's a good stopping point. Before let me just make sure. So we have hash and salt using bcrypt. Registration and authentication are that's mostly topics that we've seen before. Once you have the hashing and the salt, this is setting up forms, setting up your paths, storing information so it can persist, and things like that. And then tokens, generating a random token with at least 80 bits of entropy, and storing that in a cookie, and then storing that that token in your server somewhere that persists that associates that token with that user, and then only store a hash of that token, just like passwords. Yeah, this is the last thing I wanted to talk about. When you have this token, when you generate a token and set that as a cookie, for the same reason that we don't store passwords in plain text, you don't want to store a database of all these tokens, because if somebody compromises that database, at that point they don't even have to crack a password. They just set that cookie with that token, and now they're already authenticated. They are you at that point. So these need to be kept secret as well. So we're only going to store hashes, and whenever somebody visits our page, we're going to take the token out of that cookie, hash it, look it up in the database, and look up the username associated with the hash of that token. So a few layers of security, a few steps that we have to do to ensure some level of security with these. And then those hashes can't be broken. You got 80 bits of entropy. An attacker really has to have something that they haven't shared with the world that really breaks a lot of things to be able to break these things, to break these tokens. Those are secure. Or they go to the user's machine and just steal the token off their machine, or inject some JavaScript that is able to get that cookie and some flags aren't set right. They'd have to attack it some other way. They're not getting your database and getting it that way. So at that point, you have everything you need for this assignment. And 53, I did remember as I was saying that what the last thing that I wanted to talk about was. It is more of a discussion, so I'll set it up right now and then we can discuss it during the Q&A, so I can cut the lecture here so the video is not ridiculously long. But the setup is something we mentioned last time. I showed it off last time, but we didn't talk about it. Is why are passwords always sent in plain text?